You know, when we map out a vector space for a machine learning model, there is this fundamental expectation of, like, structural elegance.
Oh, absolutely. It's an incredibly comforting paradigm.
Right. If you are working with static embeddings, like glove or word2vec, you can actually visualize the points. You
Uh-huh.
calculate the distances, and you rely on basic linear algebra to tell you something meaningful.
Yeah, you get those clear semantic clusters.
Exactly. You have linear substructures where king minus man plus woman equals queen. I mean, it is a mathematically intuitive space.
It is. We just expect high-dimensional representation spaces to be, well, relatively uniform. We want to map relationships smoothly using standard distance metrics, like cosine similarity.
Right.
We just assume the space is being used efficiently.
But the moment you transition into the realm of deep neural language models, like the contextualized models that completely dominate the field today, that neat geometric map just shatters completely.
It really does. It becomes this geometric black box.
Yeah, the representational landscape becomes highly counterintuitive. It almost defies the basic geometric principles we rely on for vector analysis.
I mean, we see models like BERT, ELMo, and GPT-2 achieve flawless performance on downstream NLP tasks. But the actual geometry of how they position words in high-dimensional space it's remarkably poorly understood by the practitioners who deploy them every single day.
So, welcome to the deep dive. Our mission today is to illuminate the internal geometry of these contextual models for you. We are unpacking Kawin Ethayarajh's seminal 2019 paper, How Contextual Are Contextualized Word Representations, comparing the geometry of BERT, ELMo, and GPT-2 embeddings.
It's such a fascinating paper.
It really is. For those of you listening, whether you are fine-tuning these architectures or maybe building retrieval augmented generation pipelines, you already know that contextualized representations completely obliterated the benchmarks held by static vectors.
Yeah, that's old news.
Right, but this paper asks a much more profound question. What exactly is the mathematical shape of these representation spaces? Are these networks assigning, like, infinitely many context-specific vectors to a word? Or are they quietly routing tokens to a finite set of dictionary-style, discrete word sense representations?
Well, to unpack this, the paper conducts a really rigorous layer-by-layer geometric analysis.
Okay, let's unpack this. What exactly are they looking at?
So they evaluate the input layer, which we define as layer 0, and then the subsequent hidden layers of 3 distinct architectures. So that's ELMo, the base case version of BERT, and GPT-2.
Got it. And what's the data set?
The empirical grounding relies on the semilal semantic textual similarity tasks from 2012 to 2016.
Right, and using semilal is highly deliberate, isn't it?
Very deliberate, because the dataset contains instances where the exact same lexical token appears in wildly different semantic and syntactic contexts.
Like, a model might see the word dog in the sentence, a panda dog is running, and then encounter it again in, a dog is trying to get bacon.
Exactly. The goal is to see exactly where those two dog vectors end up in the latent space.
Okay, but before we talk about individual words, let's establish the baseline. Because before you can measure how contextual a specific token is, you have to understand the shape of the entire mathematical space those tokens are living in.
Right, the baseline geometry.
And the paper's first major finding regarding this baseline geometry completely upends a lot of classical assumptions.
It really does, because when we initialize a high-dimensional vector space, the default assumption is that it will be relatively isotropic.
Meaning uniform?
Yeah, isotropy means the vectors are uniformly distributed with respect to direction. They fill out the full volume of the hypersphere.
So if a latent space is perfectly isotropic, the expected cosine similarity between any two uniformly randomly sampled words should be 0.
Right, they should be orthogonal.
Hmm.
But the empirical data here reveals that in almost all non-input layers of BERT, ELMo, and GPT-2, the representations are overwhelmingly anisotropic. They do not utilize the full geometric volume available to them at all. Instead, the representations for all words are mathematically crammed into this remarkably narrow cone.
So if the upper layers are pulling all these representations together into this confined subspace, what does the math actually look like at the extreme end? Like, let's say we look at the final layer of GPT-2, layer 12. Just how narrow does this cone get?
The compression is staggering, honestly. In the early layers of GPT-2, the average cosine similarity between two completely random, uniformly sampled words is around 0.6.
Okay, which is already pretty high.
Right, but as you move deeper into the network, that anisotropy scales exponentially. By the time you reach GPT-2's layer 12, the average cosine similarity between two entirely unrelated words is nearly 1.0.
Wait, really? 1.0?
Almost perfectly aligned, yes, just by virtue of existing in that specific layer.
That's like a flashlight beam getting narrower and narrower as it passes through the layers. But wait, that seems to break the fundamental mathematical advantages of vector embeddings.
Oh, totally.
Because if we look at Aurora's theoretical work in 2017 on self-normalization, or Mu's findings in 2018, showing that simply subtracting the mean to force isotropy dramatically improves performance on downstream tasks. Isotropy is clearly beneficial.
Yes, theoretically and empirically.
So why would these highly successful state-of-the-art models abandon it? What is the actual mechanism driving them into this tiny, narrow cone?
Well, the mechanism seems inherently tied to the contextualization process itself. If you look at the input layers, layer 0, across these architectures, they are far less anisotropic.
Right.
Like ELMo's input layer, which generates character-level embeddings without any sequence context, is perfectly isotropic. The severe anisotropy only really appears as you move up the hierarchy.
So it's the attention mechanism.
Exactly.
Yeah.
The primary driver here is the self-attention mechanism in transformers, or the recurrent hidden states in LSTMs. Self-attention calculates a representation by taking a weighted average of the value vectors from the surrounding tokens.
And when you repeatedly compute weighted averages of vectors in high-dimensional space layer after layer,
the resulting vectors will inevitably have a smaller norm and will begin to point in the same dominant direction. The process of blending context fundamentally acts as this gravitational pull. It smooths out variance and drags all the representations into a localized anisotropic subspace.
which means we have a massive measurement problem.
A huge one.
If you are a practitioner trying to evaluate semantic closeness in layer 12 of a model, raw cosine similarity is practically useless. I mean, if the vectors for Apple and democracy have a baseline similarity of 0.99 just because they are in a narrow cone, then a raw cosine similarity of 0.95 between the same word in two different contexts.
Actually indicates that they are geometrically very far apart relative to that space.
Exactly.
The raw metric just becomes an illusion. So to solve this, the paper introduces definition 1, anisotropy-adjusted self-similarity.
Okay, break that down for us.
So this metric calculates the average cosine similarity between a specific word's contextualized representations across all its unique occurrences in the semival corpus. But crucially, it subtracts the anisotropic baseline of that specific layer.
Got it. So you calculate the expected cosine similarity of uniformly sampled random words in layer L, and you subtract that expected value from the raw self-similarity of your target word.
Exactly. This perfectly isolates the variance generated purely by the context.
And when you apply that adjusted metric across ELMo, BERT, and GPT-2, what happens to the self-similarity of words as they pass through the layers?
It drops precipitously.
Really?
Yeah. The higher the layer, the lower the anisotropy-adjusted self-similarity. This proves that as you go deeper into the network, the representations become intensely context-specific.
Meaning the models are not simply routing tokens to a small, finite set of discrete word senses.
Right. If the word bank merely had two static vectors, one for the river and one for the financial institution, the self-similarity would just plateau.
But it doesn't.
No. Instead, the models dynamically generate highly distinct vectors for virtually every unique sequence context they encounter.
So the representations are constantly shape-shifting. But here is where it gets really interesting. Because when you isolate the specific words that have the absolute lowest self-similarity across the layers, meaning the words whose representations change the most drastically from sentence to sentence, it is not the highly polysemous nouns.
Yeah, that's wild. You would expect words with multiple dictionary definitions, like bat or cell, to exhibit the most variance.
Right?
But the empirical data shows the exact opposite. The tokens with the lowest average self-similarity are stop words.
Stop words.
Yeah, we are talking about words like and, of, the apostrophe s, the, and to. Their contextual representations are incredibly unstable compared to nouns or verbs.
But how does that make sense from a linguistic perspective? I mean, there's no alternative semantic definition for the word the. It operates entirely as a definite article. Why is the network mutating its vector so aggressively?
Well, it reveals exactly what these models prioritize during contextualization. The variation in a token's representation is not driven by semantic polysemy. It is driven by syntactic and grammatical diversity.
Oh, I see.
Stop words appear in the highest entropy grammatical environments. A word like the can legally precede almost any noun phrase in the English language.
Right, because the self-attention mechanism is designed to absorb the surrounding sequence. The vector for the is literally forced to encode an immense variety of adjacent concepts.
Exactly. The higher the variety of contexts a word appears in, the more its contextualized vector is pulled in entirely different directions within that anisotropic cone.
Wow. So if individual words are absorbing so much of their surrounding context, if the is actively pulling in the mathematical properties of dog, what happens to the relative distances between different words sitting next to each other in the exact same sentence?
That's a great
Like,
question.
are there vectors mathematically converging toward a single point in the latent space?
So that is measured by definition 2, intra-sentence similarity. This calculates the average cosine similarity between each individual word representation in a given sentence and the mean vector of that entire sentence.
And again, strictly adjusted by subtracting the layer's anisotropic baseline.
Right, you always have to subtract the baseline. It acts as a probe to see how sequence-level contextualization physically manifests in the geometry.
And this is where the paper exposes massive architectural divergences. ELMo, BERT, and GPT-2 utilize wildly different geometric strategies to represent a sequence. Let's start with ELMo, the bidirectional LSTM. How does it handle intra-sentence similarity?
In ELMo, intra-sentence similarity increases significantly in the upper layers. The words in a sentence grow much more similar to each other, clustering tightly around the sentence's mean vector.
Which makes sense.
It does. From a theoretical standpoint, ELMo is effectively extending John Rupert Firth's famous distributional hypothesis. You shall know a word by the company it keeps, all the way to the sentence level. Because the tokens share a sequence, the bidirectional recurrent layers literally force their representations to geometrically converge.
But BERT, the bidirectional transformer, takes a different approach.
Well,
Even though it is also looking at the entire sentence simultaneously, the math plays out differently in the upper layers.
BERT is highly nuanced. As you move to the upper layers of BERT, words in the same sentence actually become slightly more dissimilar to one another compared to the middle layers.
Oh, interesting. So they start drifting apart.
They do drift apart relative to the sentence mean. However, in all layers of BERT, the average intra-sentence similarity remains distinctly higher than the baseline of random words.
So BERT recognizes that while the surrounding sentence informs a word's representation, the masked language modeling objective requires it to maintain distinct token identities to predict the missing words accurately.
Exactly. It balances the two forces.
Then we arrive at GPT-2, the unidirectional transformer. And the metrics here seem totally contradictory for a model that achieves such high perplexity scores.
Yeah, in GPT-2, the anisotropy-adjusted intra-sentence similarity hovers practically at 0 across almost all layers.
0.
Basically 0. Words in the exact same sentence are essentially no more mathematically similar to each other than two completely random words pulled from entirely different documents.
I look at that finding, and it makes me question the fundamental mechanics of the architecture. I mean, how can GPT-2 be an elite contextual language model if the words in a sentence aren't geometrically relating to one another in the vector space? Does this mean GPT-2 isn't actually contextualizing the sequence locally?
Oh no, the model is deeply contextualizing the sequence. We know that definitively because the self-similarity of individual words in GPT-2 drops near 0 in layer 12.
Oh, right, because the individual words are changing.
Exactly. But what's fascinating here is that GPT-2's success proves a vital theoretical point. High intra-sentence similarity is not a mathematical requirement for strong contextualization.
Right, because GPT-2 is an autoregressive model predicting the next token.
Yes. It encodes the sequence history into the current token state without forcing the historical tokens to geometrically converge toward a shared centroid. Two words can maintain vast geometric distances from one another in the latent space while still heavily encoding the exact same sequence context.
That is wild. Okay, so if words are constantly shape-shifting based on grammatical environments, and they aren't forming clean sentence manifolds, it makes me wonder if we could ever pin them down again.
What do you mean?
Is it mathematically possible to reverse engineer this? Can we take all this variance and compress a word's contextualized representations back down into a single, highly optimized static embedding?
So the paper tests this exact hypothesis using definition 3. Maximum explainable variance, or MEV.
MEV. Okay, how do they calculate that?
To calculate this, we take the occurrence matrix of a specific word across all its distinct contexts in a given layer. We compute the covariance matrix and apply singular value decomposition to extract the principal components.
Okay, basic PCA.
Yeah. MEV specifically calculates what proportion of the variance in those contextual representations corresponds to the first principal component.
So essentially, if you draw a single hyperplane of best fit through all of the points representing the word apple in that layer, how much of the context-specific scattering does that single vector actually capture?
Exactly. And naturally, we adjust for the anisotropic baseline because in a narrow cone, a principal component will artificially appear to explain a lot of variance, even for random noise.
Right, of course. And the benchmark results for this are basically the ultimate death knell for static embeddings as a concept. What is the actual percentage of variance captured?
After adjusting for anisotropy, less than 5% of the variance in a word's contextualized representations can be explained by a static embedding.
Less than 5%.
Yes, and this threshold holds true across all layers of all three models analyzed. There is no mathematical scenario where a single vector can capture more than 5% of the nuance spread these transformer and LSTM models are generating.
So the context is fundamentally irreducible.
Completely. You cannot compress it back into a static vector without massive information loss.
But wait, for those of you building retrieval pipelines or low-latency systems, there is actually a massive engineering application hidden in this finding, the silver lining, right?
Oh, absolutely.
Even though MEV is below 5%, the paper demonstrates that if you extract that first principal component, specifically from the earliest layers of the network, you can generate a static vector that heavily outperforms standard baseline models.
If we connect this to the bigger picture, it is an incredibly pragmatic takeaway. Running a massive 12-layer or 24-layer transformer for every single query during inference is computationally expensive.
Way too compute heavy.
Exactly. If latency is a constraint, this paper offers a rigorous shortcut. You can leverage the immense pre-training compute of BERT to generate contextualized vectors across a massive corpus, run PCA to extract the first principal component for each word, and deploy those discrete vectors as static embeddings.
And when tested on rigorous semantic evaluation datasets like Simlex 999, MN, and the Google analogy task, these PCA-extracted vectors significantly beat GloVe and fastText.
They do. You achieve structurally superior embeddings, but with the exact same constant lookup time during inference.
But the key to that implementation is that you must extract the principal component from the lower layers, like BERT layer 1. If you try to extract it from layer 12, the performance just collapses.
Right, because the geometry dictates the performance. The lower layers maintain enough isotropic volume and high self-similarity to yield a robust general-purpose vector. It functions like a generic edge detector in computer vision.
But the upper layers have collapsed into such severe anisotropy, and the vectors are so hyper-focused on specific syntactic environments that extracting a principal component yields a vector that performs terribly on traditional word similarity benchmarks. Let's summarize the geometry we've just mapped out. We started expecting a clean, uniform latent space, but we found that contextual models warp their dimensions into highly anisotropic narrow cones. As you move deeper into the architecture, the representations become fiercely context-specific, driven overwhelmingly by the structural diversity of the sequence, which is exactly why stop words exhibit the most variance.
Yeah, that was a huge surprise.
We also learned that ELMo, BERT, and GPT-2 fundamentally disagree on how a sequence should be geometrically structured, proving that convergence is not required for context. And finally, while you can never mathematically compress this dynamic variation back into a single vector without losing 95% of the information, extracting the principal components from the early layers provides a highly efficient shortcut for production deployments.
Which leaves us with a really profound theoretical challenge outlined right in the paper's future work section.
Oh, lay it on us.
So we established earlier that extreme anisotropy is an unavoidable byproduct of the self-attention mechanism constantly averaging vectors together, right?
Right.
However, prior research by Mu and others proved that forcing static embeddings to be more isotropic drastically improves their downstream performance. Currently, models like BERT and GPT-2 are achieving state-of-the-art results despite operating in a mathematically constrained, heavily penalized sliver of their available dimensions.
So the models are basically fighting with one hand tied behind their backs computationally.
Exactly the point. So the question we must ask is, what would happen if we mathematically forced these architectures to utilize the whole space?
Oh, wow.
What if we explicitly added an anisotropy penalty directly to the language modeling objective during the pre-training phase? If a model like BERT is this powerful while crammed into a narrow geometric cone, Could forcing its deep layers to push vectors apart and explore the full geometric volume unlock an entirely unprecedented level of representational power?
That is a fascinating thought. The map of these latent spaces might be incredibly narrow today, but the mathematical territory available to us is vast. Thank you for joining us on this deep dive. The next time you initialize a transformer, take a moment to visualize the extreme anisotropic geometry dictating every calculation it makes. Keep questioning the math, keep exploring the geometry, and we will see you next time.